Okay, welcome to the last of the Physics 216 YouTube videos. I hope that you've been finding them useful. So what we want to wrap up with is a final discussion of rocket motion. In the video before this one, we thought about rocket motion in two cases. One was that the rocket was somewhere in deep space, so there was no external forces acting on it. And the second was that the rocket moved through a constant gravitational field. What I want to start with today, well, actually, the gravitational field case, if you recall, what we were able to calculate is the final speed of the rocket if it was launched from rest and we assumed that the fuel was ejected with a constant relative speed, and we had to assume a certain burn time, the amount of time it took to burn the fuel. What we're going to do today is we're going to first consider what the motion of the rocket would be if the only force on it is a drag force that is proportional to the rocket's velocity. And you'll see that the approach to our solution will be slightly different. And what we'll end up doing is calculating how the speed of the rocket depends on the mass of the rocket as the fuel is burnt. And then the very last thing we'll do is we'll try to think about, well, in any practical rocket launch from the surface of the Earth, you would think that both the gravitational force and the drag force from the atmosphere would be important. And so we'll try to write down that problem. And what we're in fact going to find is that it's not simple, or perhaps it's impossible to come up with an analytic solution to that problem. And so then we'll think about some approaches that we could take to solve the problem numerically. Can we take a simple approach using a computer to write a program that would solve the problem for us? Okay, so here's the problem. A rocket travels through an atmosphere with a linear drag force, which we'll say is minus kV. K is a constant, and the force is going to act in the opposite direction of the velocity vector v. So the question is, if all other forces are negligible, can we find the speed of the rocket after it has burned all of its fuel? And so let's assume that it starts from rest. Okay, so if you recall from the last video, the starting point for these problems was that we had this expression that said that the net external force on the rocket was equal to m times the time derivative of the velocity minus capital V times m dot. And capital V is the relative speed of the ejected fuel as measured from someone in the rocket. Where this came from, remember, was just a conservation of momentum of the system, which includes the rocket and the ejected fuel. Okay, so if we draw a picture, in this case, we've got our rocket let's say it's moving with velocity v to the top of the screen. We've got our fuel that's been ejected, and that's moving with some relative velocity v compared to the rocket. And so let's really emphasize that we have a lowercase v and an uppercase v. And we're going to have a drag force that acts in the direction opposite of the velocity. And so we'll take this as the positive direction. So it's a one-dimensional problem. And so we could write that the external force is minus kv, and then that has to be equal to mv dot minus capital V m dot. Because it is a 1D problem, we can just use the sign to indicate the directions of these vectors. What we require is that the drag force act in the negative direction, and that's really just equivalent to saying that the velocity v is in the positive direction. If we're throwing fuel out the back of the rocket, we expect the speed to be increasing, the rocket speed, so v dot is positive. And then the velocity capital V is opposite of the positive direction, so it's a negative. So we have minus capital V, which is minus V, or plus capital V m dot. Okay, so what we're going to do in our approach is that we're going to assume that we burn fuel at a constant rate. So assume that we burn fuel at a constant rate. And really what that means is that we're assuming that m dot is equal to a constant. The first thing that we'll do is we'll just divide by minus k. And so we get minus m over k v dot minus big V over k m dot. Clearly, we're going to assume that the speed of the rocket v dot is, v dot is changing, so the rocket is increasing in speed. So clearly, it must be the case that the speed of the rocket is a function of the mass of the rocket. So you think of it this way: if we start the rocket from rest and it's full up of fuel, then we have v equals 0 and the mass is large. And then as we burn that fuel, the mass is decreasing and the speed is increasing. And so there must be clearly some kind of dependence of the speed on the total mass of the rocket. Okay, so then what we have then is v dot is d by dt of v, which is a function of mass, and by chain rule, that's equivalent to dv dm dm dt, which is just m dot dv dm. So this is by chain rule. This is going to be useful because then what we'll have is an m dot in both of our terms on the right-hand side. And we've already assumed that m dot is a constant. So let's make that substitution. So for v dot, what we're going to do is we're going to take this and place it into v dot. Okay, so what do we end up with? V is equal to minus m over k, and then we have an, let me write it this way, dv dm m dot. So that's what we're replacing v dot with. And then we have minus big V over k m dot. Just rearranging some of the terms a little bit, or some of the factors in these terms, we have minus m over dm, and then we have a dv, and then we have an m dot over k, and we have a minus v m dot over k. So both of our terms have an m dot over k. The last thing, well, sorry, it's not the last thing that I'll do, but the next thing that we'll do is we'll divide by the speed of the rocket, divide by little v. And what we end up with is 1 is equal to minus m over dm, dv over v, m dot over k, minus big V over little v, m dot over k. Okay, so we're going to define a new quantity, and the quantity that we're going to define is going to be alpha. So alpha is going to be defined to be minus m dot over k. And so let's recall that, first of all, one is that m dot is equal to a constant. That's what we assumed was going to be the case. And k is also a constant. It's our drag coefficient. And so this alpha is constant. So if m dot is a constant and the drag coefficient is constant, then alpha is equal to a constant. The second thing that I want to recall is that m dot is dm dt, so it's how the mass of the rocket changes with time. We're burning fuel, and so we're losing the mass as we eject the exhaust. And so that means m dot is less than 0. M dot is negative, and so that means because alpha is proportional to minus m dot, alpha is positive. So alpha is a positive constant. Okay, so alpha is a positive constant. Okay, so with that definition of alpha, then our expression that we've been working on becomes 1 is equal to m over dm, dv over v, alpha is the minus m dot over k, and then we get plus big V over little v times alpha. So we could start to do some rearrangements. What I'm going to do is I'm going to subtract off this term and bring it to the other side. So we'll end up with a 1 minus that term, and we'll have an m dm dv over v alpha is equal to 1 minus big V over little v times alpha. Or solving for dm over m. So what we would have to multiply by dm over m, and then we would have to divide by 1 minus big V over little v times alpha. So we would get alpha dv over v divided by 1 minus big V over little v times alpha. Multiplying the right-hand side of this expression by v over v, we could equivalently write that alpha dv, that dm over m is equal to alpha dv little v minus big V times alpha. Let me put the alpha over here. So we would get, alpha times big V. Okay, good. This is useful because this is an expression that we could integrate. On the left-hand side, we have only a function of mass, and so on the left-hand side, we integrate from some initial mass m0 to some final mass after we've burnt our fuel. And then on the right-hand side, alpha is a constant, so we take that out, and we have the integral of dv over v minus alpha v. And if we start our rocket from rest, and we want to know what's its final speed after we've burnt a bunch of our fuel. Okay, so the integral of 1 over m is the ln of m, and so we would end up with the ln of m over m0. Over here, what we might do is we might make a change of variables. Let's say u is equal to v minus alpha times big V, so that when little v is equal to 0, u is equal to minus alpha times big V. When v is equal to some final speed after we burnt some fuel off, then u is equal to v minus alpha v. Du is equal to, alpha is a constant. We're going to assume that we eject fuel at a constant relative speed, and so du is just dv. So if we make that change of variables, what we have is that the ln of m over m0 is equal to alpha. The integral of u is equal to minus alpha times big V to v minus alpha times big V of du over u. So we'll just get another ln function. So this is going to be the ln of, what will it be? It'll be the ln of v minus alpha v minus the ln of minus alpha v. So we get, if we combine those two, that's what we get. So let's see, let's multiply top and bottom of the argument of the ln by a negative sign. So this would be alpha v minus v over alpha v. Okay, so what we have then is ln m over m0 is equal to alpha ln of alpha v minus v over alpha v. Okay. So what we've got then is, let's divide by alpha. I don't know how to get rid of this notification. Oh. Sorry, that dentist appointment is canceled. Our dentist is closed. Okay, so where were we? We were dividing by alpha. Alpha v minus v over alpha v. Okay, so one nice properties of lns, if we had something like a ln b, we could write that as the ln of b to the power a. So I'm going to do that, and I'm going to say that this is equal to the ln of m over m0 to the power 1 over alpha. This is convenient because now what we have is the ln of something equals the ln of something else, and so that something must be equal to something else. So it must be the case, therefore, that m over m0, 1 over alpha, is equal to alpha v minus v over alpha v. What we said we wanted to do is we wanted to solve for the speed of the rocket. And so the speed of the rocket is right here as a function of the mass as we burn that fuel off. So let's solve for the rocket speed, v, and then we'll be done. So let's see, what are we going to have? We have that alpha v is equal to alpha v, let's do it this way. Alpha v minus v is equal to alpha v m over m0 to the power 1 over alpha. And so therefore v is equal to alpha v, and then it must be 1 minus m over m0 to the power 1 over alpha. And that is it. So this is the speed of the rocket as a function of its mass. Let's remind ourselves that alpha was equal to, let's just go check. It was minus m dot over k, I believe. Yeah, minus m dot over k. Where m dot is the rate that we burn fuel. M dot was negative. And k is the drag coefficient due to the atmosphere. Okay. We could also maybe just remind ourselves is v is the relative, let's say it's the speed of the ejected fuel, or it's the speed of the ejected exhaust relative to the rocket, to an observer on the rocket. Okay, good. So let's see if we can go a bit further. The next thing we're going to do is we're going to say, well, what if we had a drag force and a constant gravitational field? That sounds like it's simple enough to incorporate into our kind of starting point of our rocket analysis, because we just have to modify the F external. And so what we're going to attempt to do is we will first try to do the type of analysis that we just did for the drag force, but we'll just include the gravitational force as well. And what we'll find is that it's going to lead to some difficulties. So let's start that way. So what if we have both a drag force and a gravitational force? So what if we have both gravity and drag? Okay, so we've solved for the case of gravity and we've solved for the case of a drag force independently. So let's combine them. So our starting point is to return to the fundamental rocket equation. And so that fundamental equation was the result of conservation of momentum, which said the external force on our rocket was equal to mv dot minus v m dot. Okay, and so we'll do the usual thing. We'll draw ourselves a rocket and we'll draw our exhaust, and we'll say that towards the top of the screen is going to be positive. So this rocket speed is positive, and we're expecting as we burn fuel, the V dot is also positive. Gravitational force acts in the negative direction. The drag force acts in the direction opposite of the velocity, and the relative velocity of our exhaust is also negative. And so when we combine all those things, we have a minus mg and a minus kv is equal to mv dot plus v m dot. I'm going to call this equation star because we're going to come back to this thing. So let's put it in a red box so that we can find it when we need to. Okay, so like I said, what we're going to try to do is we're just going to try to proceed with the type of analysis that we just did for the drag force. So we use, again, the fact that we expect the velocity of our rocket to be a function of mass, which then by chain rule led to v dot being written as dv dm m dot. So we make that change and we get minus mg minus kv is equal to m dv dm m dot plus v m dot. Okay. So let's divide everything by a minus k. mg over k plus v is equal to minus m dm dv m dot over k minus v m dot over k. We will eventually, or very shortly, we're going to define that parameter alpha as minus m dot over k, like we did before. The other thing we did is we divided by a v. So we're going to get an m over k g over v plus 1 is equal to minus m over dm dv over v m dot over k minus v over v m dot over k. Okay, so alpha is defined as minus m dot over k such that m over k g over v plus 1 is equal to alpha m over dm dv over v plus alpha v over v. If you look at this expression, it's identical to one that we had for the drag force, except for this first term on the left-hand side, right? In fact, if all you did is you said, okay, our constant gravitational field is g equals 0, then you would get exactly what we had in our previous analysis of just the drag force. It's going to turn out that this additional term is important. It's going to cause problems for us. Okay. Anyways, what we did next is we tried to isolate for dv over v. So what we'll do is we'll take the alpha v over v and we're going to subtract it off. And so we'll subtract it off and bring it over to the other side. When we do that, we'll get an alpha m over dm dv over v is equal to, well, what do we have? 1 plus mk g over v. That's our new term that we didn't have before. And then we would have minus alpha v over v. Okay, so this is equal to what? 1 plus, there's a common factor of 1 over v, and so we would get an alpha big V, and then we'd have a 1 over v like that. So then we could do something like alpha m dm dv. So let's multiply by a v, and so we would get little v plus m over kg minus alpha v. And so finally what we could do is we could say therefore what? Let's solve for dm over m. So we multiply by dm over m, and then we divide by everything that's on the right hand side. And so we would be left with alpha dv divided by v plus m over k times g minus alpha v. Again, if we set g equal to 0, this is something that we had before, and what we could do is we could just integrate both sides. But we have a problem at the moment. The problem is we have a factor of the mass here on the right hand side. Before, what we had is we had all of the terms involving mass on one side, on the left hand side of our equation. We integrated that and we get the ln of m. And then we had only on the right hand side we had constants and some and just velocities and dv's. The issue here is that this mass is a function of velocity. So if we wanted to integrate from some initial velocity, say v equals 0, to some final velocity, then during that entire integration, the value of this mass would be changing. And we don't know how it changes with velocity. If we knew that, then we wouldn't be solving the problem in the first place. In fact, what we're trying to find is the relationship between velocity and mass. And so we don't know the dependence of m on v. So we cannot integrate the right-hand side because m depends on v. We're trying to solve for the relationship between m and v. Therefore, the dependence of m on v is unknown. And so it's not possible to separate the mass variables and the velocity variables in a straightforward way. straightforward way. So what we need is we need a new approach. And the new approach is that we're going to attempt to solve this problem approximately using numerical methods. And it'll turn out to be actually not so difficult. So the new approach is to attempt to solve our problem approximately using numerical methods. And I think what we'll see is that although our solution will always be an approximate solution, we can make the approximation basically arbitrarily close to the exact solution in a simple way. And so let's look for that as we do this. So as I advertised, what we're going to do is we're going to return to equation star. And so we put that in a red box, and there it is. So it's minus mg minus kv is mv dot plus vm dot. Okay, so we'll rewrite equation star. Minus mg minus kv is equal to m, and it was v dot plus v m dot. Okay, so what we're going to do is we're going to say v dot is just a change in velocity in some time interval delta t. And m dot is a change in mass in some time interval delta t. And so the reason that our solution is going to be approximate is because we're going to choose some step sizes, right? An exact derivative is an exact value for v dot, for example, is you would plot v as a function of time, and at whatever time you're interested in, you draw a tangent line to that curve, and that the slope of that tangent line is v dot. What we're going to do is we're going to approximate v dot as a finite change in velocity divided by a finite change in time. The reason that we'll be able to make our solution basically arbitrarily close to the exact solution is because we could always shrink our choice for, say, the step in time delta t to be as small as we like. Okay, so anyways, if we make that change, then we have minus mg minus kv is equal to m delta v divided by delta t plus v delta m over delta t. You know, equation star is basically what we call the fundamental rocket equation, where we just picked something for the F external on the left-hand side. In our case, it was a gravitational force and a drag force. Okay, so if we multiply by delta t, then what we end up with is minus mg minus kv delta t is equal to m delta v plus v delta m. One of the things that we assumed is that the burn rate of the fuel was a constant. So if the burn rate is constant, m dot is delta m divided by delta t, then what we could do is we could write delta t is equal to delta m over m dot. All right, so let's do that. We would get minus mg plus kv. Delta t is delta m over m dot, where m dot is going to be some constant. And so that equals m delta v plus v delta m. Okay, so what I want to do is I want to solve for delta v. This is going to be the change in the rocket's velocity due to a change in mass delta m. So we've burnt some fuel so that delta m is some negative number, and what we're really solving for is, as a result of that burned fuel, what is the change in velocity? Okay, so let's see. M delta v is equal to minus mg plus kv delta m over m dot, and then we're going to minus v delta m. Okay, so that delta v is equal to minus, let's see, I'm going to do it delta m over m times v. So I wrote the second term on the right-hand side first. And then we have minus delta m over m dot. And then we have to divide by m. So we have mg divided by m, which is g. And then we have a plus k over m times v. Okay, so this is one of the important results here. So what we're going to do is we're going to solve this problem in small steps of equal changes in mass that are negative. Another way to see that this is clearly an approximation is that if we assume we have a small step, delta m, what we're going to do is we're going to treat some of these variables, like the mass of the rocket and the speed of the rocket, so there's mass appears again, as constants during that small step. So let's say our rocket weighs something like 10,000 kilograms, and then we're going to burn 1 kilogram of fuel, and we want to know what's the change in the velocity. Well, we're going to assume that the change in velocity is small enough that we can treat v as being approximately constant when we burn that 1 kilogram of fuel. And we'll also treat m as being approximately constant, right? If we had a 10,000 kilogram rocket and we burn off of fuel, 1 kilogram of fuel, the rocket's still almost 10,000 kilograms in mass. Okay, so the implementation in our numerical solution is the following. So the numerical implementation would look something like, we would have some initial conditions. So the initial conditions are, say for step I is equal to 0, we would have, say vi is equal to 0. Maybe we're launching our rocket from the surface of the Earth, and mi is going to be some initial mass, whatever it is. We're also going to use fixed values of m dot, the rate that we burn the fuel, and we'll use a fixed value of v, the relative velocity of the ejected exhaust. And in fact, maybe it's worth mentioning that we're going to use a fixed value of the drag coefficient, k, and a fixed value of the gravitational field, g. Why is that worth mentioning? Well, if you really think about launching a rocket from Earth's surface, near the surface of the Earth, the atmosphere is relatively dense, but as we get further and further away, the density of the atmosphere will go down. And we would expect, therefore, that the drag coefficient should go down as well. I mean, it may be even more complicated than that, because a drag force proportional to velocity is typically valid for low speeds, and then it usually will transition over to a drag force proportional to the square of velocity once you get to high speeds. We're going to neglect all of those issues, but it is a limitation of our solution. Furthermore, the gravitational acceleration g is not constant as we get further and further away from Earth. Again, we would expect the gravitational force would get weaker, right? The gravitational force is proportional to 1 over the square of the distance between the two interacting objects. And so as our rocket gets further away from Earth's surface, say a significant fraction of the Earth's radius away, then the gravitational field will not be a constant. Okay, so what we'll do then is we'll have those initial conditions, and then what we'll do is we'll calculate the change in velocity for step I, and the change in velocity is just going to be it'll be equal to minus delta m over the mass at step I. And again, we're going to assume that the change in mass is so small for each individual step that we can treat mi as a constant. So then we would multiply by capital V, and then we would subtract off the delta m over m dot, and we would have to take a g plus k over mi times vi. What I should have said is that we also have to, in this first step, is we're going to have to pick a value for delta m, and it's going to be some small negative number. Okay, so we calculate that delta vi. Step 3 is, once we know the change in velocity, we'll say, okay, the velocity at step I plus 1 is going to be equal to whatever it was at step I plus that change in velocity. We also have to take care of the fact that the mass of our rocket needs to be updated. Initially, at step I, it had mass mi, and then there was a change in mass where this delta m is going to be a negative number. So after you've done that, you would go back and you would say, do step 2 again, and then do step 3 again, and go back to 2, and go back to 3, go back to 2, go back to 3, and you would just iterate these steps over and over again until you reached a point where the mass becomes equal to whatever the final mass is. Maybe you've burnt all of your fuel and the final mass is just equal to the mass of the fuel containers or the rocket plus whatever the mass of the payload was. So we're going to iterate steps 2 and 3 until the mass at step I is equal to the final mass. So all fuel is burnt. For each of these steps, we could keep a tally of the MI and VI values. And then what we could do is we could produce a plot of VI as a function of MI for all steps I is equal to 1 to however many steps there were. Okay, and so that would be the solution of our problem. And what I'd like to do in the next few minutes is just show you an implementation of this. And so let's see if I can make this work. I should have this thing loaded up. So what I'm going to show you is a implementation of this numerical solution done in Maple. So if you're interested in this, this PDF that I'm going to show you is already on the course website, and so too is the actual Maple file. So if you wanted to open that and play with it and modify it and do some things, you can. So the first thing that I'll point out is that here M0 is the initial mass of the rocket plus the fuel, and what we're going to assume is that we're going to run this code until we reach our final mass, which was chosen to be 10% of the initial mass. So if our rocket, it looks like we chose 100 kilograms for our rocket, we're going to assume that 90% of that is fuel. The step size, this is the step size delta M, and you'll notice that it's negative. So it's minus 2,000 kilograms. And so what's important, of course, is that the step size delta M be small relative to the initial mass. And in fact, it should also be small relative to the final mass. So the final mass is 10 to the 4, which is 10,000. And so our step size is 20% of the final mass. Okay, this is the speed of the ejected exhaust as measured by an observer on the rocket. Here we're starting from rest, so we start from rest. So G is, so this R is the burn rate of the fuel. And so let's see, let me go back and just take a look at this thing. Yeah, so R is delta M over, right, okay, mg of, okay, R is the, it's the rate with which we burn the fuel. So it's the burn rate of the fuel. Okay. So the first thing we're going to do is we're going to assume that G and K are equal to 0. So no drag, no gravity. No drag, no gravity. Why are we doing this? We're doing this because this is a problem that we solved exactly. And so what we're going to check is that when we solve our problem numerically, we want to verify that our numerical solution is equivalent to an exact solution for a problem that we've already solved. And so here's just the loop where this is really just going to iterate steps 2 and 3 that we wrote down. So we're going to iterate from m0 to the final mass by steps of delta m. And for each step, we're going to calculate the change in velocity, and then we're going to update the velocity. It's going to be v plus the change in velocity, and that's it. So our change in mass is already taken care of by our loop condition, and we just run the loop. We keep a running list of the mass and the velocity, and then we produce a plot. And we're also going to plot the exact solution that we already solved for a rocket with no external forces applied to it. And so here's the results. So the data points are the numerical solution, and the red line is the exact solution. And you can see they're not identical, but if we were to go back and rerun this code where we set the step size dm to be smaller than 2000, if we made it, instead of 2000, if we made it equal to 20, then our approximate solution would get closer to the exact solution. And we could make dm arbitrarily small so that our numerical solution becomes arbitrarily close to the exact solution. Okay, so that worked. In the next case, everything's exactly the same, but we turn on gravity. So we have gravity, but no drag. Again, this is a problem that we've already solved, so that when we run the exact same simulation, we can compare our numerical solution to the known exact solution. And so the blue line is the exact solution, and these are obviously our numerical solutions. And they're, again, quite close. This red line is no drag, no gravity. And so we get the result that, of course, if we turn on a force that opposes the motion of the rocket, such as the gravitational force, then we expect that our final speed, once we've burnt our fuel, is less than what it was before. So in this plot, this is the rocket speed, is the vertical axis. So this is the rocket speed. And here is the rocket plus fuel mass. So out here, this is the point that the rocket is launched, right? Where we have the full 100,000 kilograms of the rocket plus fuel, and the speed starts at 0. It starts from rest. And then as we burn fuel, we increase the rocket speed. And so this is, over here, is at burnout when we get to a final mass of, I guess it's must be 10,000 kilograms after we burnt all our fuel. Okay, so that's good. Next, we do no gravity, and we turn on drag. Drag is on. We run the exact same simulation, and again we have an exact solution to compare to. And when we do that comparison, it's the green line is the exact solution, and the dots are our numerical solution, and again we get good agreement. And so this is no drag, no gravity. This is no drag, but gravity is on. Gravity is on. And this one is no gravity, but drag is on. And so, of course, the last thing to do is to turn on gravity and to turn on drag. We run the identical simulation, but this time what we can't do is we can't compare it to an exact solution because we don't have one. But because we've done all these checks, we've checked the case of F external equals 0, and we've checked the case of only gravity, and we checked the case of only drag, and they all worked well. So we have some confidence that our code is doing what it should do. And so let's go and take a look at the solution when we have both. So these points are the numerical solution for drag and gravity. And it should be satisfying that what happens is that the final velocity at burnout is less than all of the other three cases. And it has to be, because now we have two forces that are opposing the motion of the rocket. The other thing that's interesting is that at low speeds, the drag force is not important because it was proportional to, well, the drag force was equal to minus k times v. And so if v is small, then the drag force is small, and you can see what happens is our solution follows the blue line, which is the gravity-only solution. Once we reach a high enough speed, somewhere above this point, then drag starts to become important, and the speed of our rocket slows down compared to what it would have been with only gravity. So this is really where the effect of drag becomes important. Okay, so I just wanted to show you, I'm not going to go through the details of this, but you can actually just write down a differential equation in Maple and tell Maple to solve it. And so this is Maple's numerical solution of our differential equation when we have both drag and gravity turned on. And so its solution is the pink line. And you can see that Maple's pink solution is very close to our numerical solution, and so that's satisfying as well. The benefit, of course, of writing our own way to solve the differential equation approximately is that we know all the details of the solution, and so it makes sense to us. I just wanted to show you one other thing where I'm going to run this program again, but what I'm going to do is the only thing that's going to change is delta m is going to go from, it was minus 2,000 before, to minus 10. So we make our step size really, really small. And if we make our step size really, really small, then our numerical solution exactly matches Maple's numerical solution of the differential equation. And so that's what I meant by we could make our solution arbitrarily close to Maple's, or arbitrarily close to what the exact solution must look like. Okay, so that's good. And so what you can do is you can look at this code at your leisure whenever you want. And I think, let me just check one thing. So we had a dm over r here, and we have an r over dm. So I think this one is a mistake. It turns out not to be a problem because in this solution, g is equal to 0 and k is equal to 0. So this mistake doesn't affect it. But you may have seen me notice that I hesitated here and I was getting confused. Notice that over here, it's inverted. So when we actually make use of this, it's a dm over r. And so why is that important? It's because what we said in, if you look back at our notes, delta vi was equal to minus delta m over mi v minus delta m over m dot g plus k over mi vi. Okay, and so you can see some things. You can see the first terms are identical. So minus v dm over m. So this is minus v dm over m. So that's the same. And then we have a mg over m is g. And then we have kv over m, kv over m. And then we have delta m over m dot. And so this is r. What I said about r being the rate that we burn fuel at was correct. It's just in this first example, the thing is inverted, so that's unfortunate. However, the result is right because here we had g equals 0, k equals 0. In all the other instances, it's dm over r and dm over r and dm over r. Okay, good. Yeah, so when we actually used that term in our solutions, we had it right. So anyways, that's where I'm going to stop. I hope you, like I said, I hope you found the video lectures useful. And keep an eye on the course website for any additional details about, the final exam and things like that. And I wish you all the best. Thank you very much.